Okay, guys, so from wonderful zebrafishes, we are moving to neutrinos. And to start with this, and to gauge the basic from where I need to start, there is one quiz question coming up. And the quiz question is, what's the similarity between zebrafishes and neutrinos? So do they have a similar weight? Do they approximately move at the same speed? Are they able to go back to the previous state? Or there was some fourth option that Cornel is typing to, I think, that I now lost.
Oh, yes. I just launched the poll.
Okay, great. Then we'll see the answers probably after I go to my first slide. So, okay, what do you have to endure in the next 10 minutes? So first, I'll go over what are neutrinos, then how do we see neutrinos, and what does it mean to see neutrinos? Oh, wow. We have 100% the correct answer. This is great. How many votes do we have, Cornel?
We have a total of 12 votes, and all 12 of them were correct.
Okay, I was assuming that maybe I was the only one.
Maybe we can skip this talk, Wouter.
Yeah, I think I will go straight to the slide with the equation. So that's great. Okay, so after we know how neutrinos look like, we'll ask the question if they have mass and how similar the mass is actually to the average zebrafish. And then how does the balance look like that you would put a neutrino on? While you were looking at this wonderful slide, every second, approximately 100 trillion of these neutrinos passes through your body. And although they are very weakly interacting, they actually play a very important part in the story of our universe. So let's go back 100 years. The universe was basically made up of protons, neutrons, and electrons that we were studying, and that was able to explain everything. So why do we actually need more particles? So the study of the neutrino began by a process called beta decay, which is a process where the nucleus of an atom changes from a neutron to a proton. So from a neutral particle to a positive proton particle, which happens in every kind of natural decay, but also other processes. And to have charge conservation, if you create a proton, you will also create an electron. So then you're happy with charge conservation. You actually have two other laws in physics. One is conservation of energy, and another one is conservation of momentum. So if the neutron is standing still, then your proton can move one way and your electron has to move another way. Now it turns out if you write down these three equations of charge conservation, energy conservation, and momentum conservation, there is no solution. Well, there is a solution, and that's why they proposed another particle, which was the neutrino. They said at that point, in 1930s, that they created a particle that was impossible to see. It took us effectively 30 years to finally catch a neutrino. So, okay, we have protons, neutrons, and electrons. Why do we actually care about beta decay? Is beta decay is important? Yes, it is. The most basic example is the sun would not shine without beta decay. In the fusion cycle, which goes on at the core of the sun, neutrinos are actually very important to do this transition between protons and neutrons and actually create helium, which is a fusion reaction, which makes the sun shine. And this also means that the sun is actually a source of neutrinos. So how do we see neutrinos? Neutrinos interact very weakly. When I mean interact very weakly, I kind of mean it. If we would want to stop a neutrino, let's say we are able to create one neutrino in a given direction, then we would be able to put a lead bar inside of in front of it. For most types of radiation, if you would put a lead bar of a few centimeters, you would be fine. You would have stopped everything. To stop a neutrino, you need to put a lead bar from here till the nearest star, so approximately 1 light year, and then you would be able to stop half of the neutrinos. So the other half would still escape, but at least half of your neutrinos would be stopped. So this makes them completely unique. There is no other particle who could even think about traveling through 1 light year of lead. So if we want to actually observe them, we do not have lead bars that are 1 light year long, so we need to think harder. And one characteristic is we need to go very clean. Everything which is not clear, every impurity will create signals that will be larger than our neutrinos. So therefore, all neutrino experiments are basically clean rooms. A second one is, even if we have a clean room on Earth, we are still bombarded by all kinds of atmospheric radiation and cosmic radiation. So the Earth is all the time flies through a universe that is a very aggressive environment, and there are loads of particles from outer space coming in all the time. And we would see those particles, and we want to see neutrinos. So therefore, we go underground. So the picture here is a sphere, which is in Canada, which is put in an old mine, and this is 2,000 kilometers underground. So if you go 2,000 kilometers underground and you have 2,000 meters, I'm exaggerating. So if you go 2,000 meters underground, then you actually manage to reduce the radiation that comes through, because the Earth above it stops most of it, that you can actually start looking at neutrinos very clearly. To give a size, there are on the background some people working over there. So this is a sphere which is filled with all kinds of cameras, and then they submerge this in a liquid, and then they look at the light coming from the neutrinos. So this already gives my third point, actually. If you want to see neutrinos, you better go big too. Like the larger you are, the more neutrinos you're going to see. The detector you're seeing here is actually a cylinder, which is 60 meters high and about 30 meters wide. And it's located in Japan in the heart of a mountain. So also about 1.5 kilometers under the top of a mountain. And you can actually see people inspecting the quality of the camera. So all these balls that you see, in total there are 20,000, are cameras looking at the inside where a neutrino might pass through. So sometimes they lower the water level in there. It's actually not just water, it's hyper pure water, such as clean room water. They lower the water level, and then with an inflatable boat, you can actually go around to check which PMTs, that's how we call these cameras, are broken, which are functional, and do some repairs. I have not been lucky enough to go on there with my inflatable, but I do have some friends who actually were. So what can you actually then see if you catch these neutrinos? You can think of neutrinos in a similar way as if you think of light. So when we see, what it means to see is actually photons, light particles are sent out by objects. We detect them with our eyes and we form a picture. With neutrinos, you can do the same. The difference is just that the thing you want to see needs to emit neutrinos, and the detector you want to have need to be very deep underground, very clean, and very big. And this is a picture of the sun, which I told in the beginning emits all of these neutrinos in neutrino light. And this actually tells us that neutrinos can be used to do astronomy. We can see the sun with them. And one of the most beautiful experiments on the world, I think, is Ice Cube experiment. And this is an experiment on Antarctica, and it actually uses the Antarctic ice sheet to look at neutrinos. So this is just the surface of the detector where people live and where the data is stored. But the ice sheet on Antarctica is 3 kilometers deep. So what they did is they lowered 5,000 cameras in the ice using heat drills. So they heat up the ice with some weight. The weight sinks to the bottom of these 3 kilometers. Then they put in strings with thousands of cameras on. And then they the ice refreezes, and they look at signals that these cameras are seeing from the whole ice sheet. So they basically have a detector which is the size of kilometers by kilometers by kilometers, looking at neutrinos to observe the universe. Okay, so this tells us a bit about what a neutrino is, what you can look at it with it, and that they are everywhere. So my question is actually, do neutrinos have mass? Neutrinos come in 3 flavors, which will be important. So we have electron flavor, muon flavor, tau flavor, and what exactly which is doesn't matter, but there are 3, and those 3 flavors can actually change between each other. And this is again something that makes neutrinos unlike any other particle. If you have a proton is a proton, it cannot change in a neutron because there is charge violation. Otherwise, other types of violation would occur too. But neutrinos in some way can change from one side to another. And we actually understand it kind of. And it has to do with the fact that we can tell the story about neutrinos in 3 flavors, but we can also tell the stories about neutrinos in 3 masses. And actually, these are linked to each other. So if I say an electron neutrino, I actually mean a bit of a neutrino with mass 1, a bit of a neutrino with mass 2, and a bit of a neutrino with mass 3. And therefore, all these neutrinos are combinations of each other. And now we are going to get a bit in quantum mechanical superposition, but don't worry too much. A particle, if it's very small, can also be seen as a wave. So there is this particle-wave duality. And when we look at particles as a wave, we get all the characteristics that waves have. And if you have waves that interact with each other, you get certain places where they get amplified and certain places where they actually disappear at all. And if you send out in the universe different neutrinos with different masses, depending on how they are traveling and in which direction and how they connect to each other, at different places in the universe, this might look like an electron neutrino, and then a muon neutrino again, and then an electron neutrino again. So this behavior is called the neutrino oscillation, and actually got a Nobel Prize in 2015. So let's go to the equation now, because everyone got the introduction question perfectly right. So what do we know now if these neutrinos oscillate? So we do know they have a mass. So why are you still interested in their mass as a researcher? So this is the equation which tells you what is the probability that I start with neutrino alpha and it goes to neutrino beta. So what you get here is a bunch of matrix elements, which are all these unitary U's in there. And they tell you how much of a certain flavor has to do with a certain mass state. But the important thing here is what is the dependence on how a neutrino travels to space. And this depends on its mass. So you see the sign there, and you know a sine wave is an oscillation. So that's what dictates the oscillation. And what actually matters for the oscillation, there are 3 parameters in there, which is the length, the energy, and then the mass difference. So if we study all these oscillations, like I actually did in my PhD, we learn a lot about neutrinos, but we only learn about mass differences. We have no clue what the absolute mass is. So therefore, the absolute mass scale of the neutrino is actually a mystery. There is no way that I talked about yet that we have an idea what it is. We do know one thing, because we have classical methods to look how heavy some object is. And we use these methods, which mainly depend on looking at the energy that a particle has, and then using Einstein's relation to relate energy to mass to find out the masses. And we did this for all these particles who are on the right, like the electron is over there, the blue and the green ones are quarks, which are building blocks from protons and neutrons. And we found that they were very light, like 10 to the minus 25 kilograms or something. But when we try these tricks with neutrinos, we only find upper bound. We always get the answer, the neutrino is actually lighter. The neutrino is actually lighter. This plot is even out of date, so we know that the neutrinos are even 10 times lighter than this picture is telling. But effectively, the conclusion is 1 zebrafish is heavier than 10 to the 33 neutrinos. So they are extremely light, and we have not yet a clue how light they are. So why do we want to know how heavy they are? Isn't it fine if they are so small and so light? Does it even matter that they have a mass? Well, it kind of does, and that's because our universe is now described by something we call the standard model. And the standard model is actually crazy accurate. So a lot of objects, it is predicting with as many digits as we can measure. And sometimes physicists get annoyed by the fact that it's so precise, because if it's so precise, you can't make progress because everything seems to work out. We found the Higgs particle too. It also didn't tell us anything about new physics, but there is a big black box there. There is a lot of stuff we don't know. Let's focus on the pie chart here on the right. And we see that most of the universe is actually built up of gas. So intergalactic gas, hot gas, cold gas. gas in galaxies, and so on. There is a lot of stars, and an even smaller amount is planets and zebrafishes on these planets. But then we look at the universe in gravity, and we see that this doesn't match. So everything we know about, everything that we can observe, is actually 5%. And the rest of the universe exists of stuff that we call dark matter and dark energy. These names tell already we have no clue what we're talking about. And one way to access this is going to be the neutrino. The neutrino is already physics beyond the standard model, and is currently our only pathway that we have to look into physics, which is actually in these dark sectors that are called dark matter. So therefore, it's of course ultra important to know how heavy the neutrino is. So how does a balance look like if all the other balances fail? So this is the currently best balance that we have. It's a balance, so it is in Germany, and it's, as you could have expected from this story, very big. So what you're seeing here is a big cylinder that was being transported from the place where it's fabricated to Karlsruhe in Germany, where it's put underground and now has been measuring for 10 years. And the limit of the sensitivity is also to the mass, is also its size. So the bigger you make it, the better it is actually. And the limit was dictated by how they could transport it to the place to put the experiment. So they calculated that they had like 20 centimeters okay and could move through everything. And I think if this was not in Germany, this would not have worked out, but somehow they managed to squeeze it through everything. So this brings me actually to my current work. And this is finding a way to be smarter in measuring the mass of the neutrinos. So this is a schematic of how we are trying to approach this problem. And I'll start in the middle. So in the middle, remember the second slide or something where I talked about this beta decay, which is this atom which is decaying into an electron and a neutrino and a proton. Well, here you have tritium gas, which is the T2 gas, and that actually is a beta decay source. So this will decay into an electron and a neutrino. Now, I also told you that catching the neutrino takes 1 light year of lead or crazy big detectors which are underground. So basically forget about it, you stand no chance. But catching an electron is actually quite easy. And the physics tells us if we know the electron extremely well, it will tell us something about the neutrino. And if we catch millions of these electrons that we study very well, it will tell us the mass of the neutrino. So this is how the balance looks like. You're doing an indirect measurement. You're trying to focus on the electron to learn about the neutrino. So to study this electron, you need to make sure that it doesn't escape, because it flies, of course, near the speed of light. And for that, you will build a superconducting magnet. So think a bit about an MRI, but in the middle of the MRI, there is not a human, but there is some kind of volume where there is this gas. And then if you catch this electron in a magnetic field, it will start rotating and it will start emitting radiation. This radiation we can catch. And again, if you do the mathematics, this radiation will actually tell us something about the electron and just the thing that we need to know to find out the neutrino mass in the end. The problem here is that this radiation will be extremely weak, so that you need super sensitive detectors. And therefore you need these amplifiers. And that's especially what I'm working at MIT. That's on developing a new type of these kind of amplifiers that can detect microwaves that are too faint to see with anything we have currently. And one of the reasons that I'm very interested in this is that it can be used to measure the mass of the neutrino, but it can also just detect any type of microwave we have. And microwaves are very important for a wide set of reasons. And this specific device is also used to read out quantum computers. More specifically, the elements of a quantum computer is a qubit, and such a qubit will emit microwave radiation that is just read out by the exact same device. So this device, for me, is kind of what brings a lot of different physics together and bridges the gap from a very abstract problem that still has a very elementary meaning for our universe to something which is actually directly applicable and might be very important in our future directly for us, such as quantum computers. And there is like one thing that you always know with neutrinos when you start looking at them. You might find things that you don't want. You might fail in to measure what you will, but they will tell you something because we don't understand them completely yet. Okay, thank you.